Now, after reset, contents of ECX depends on result power up self test. So this power up self test will be initiated by 80386, and that self test result will be stored in the EX file. So this self test may be requested externally. So how user can request? So by asserting busy bar at the end of reset. So by the end of reset, it is expected that busy bar, if you make it low, in that case, we can initiate or request for self test, right? And as a result, it will give you the value in EAX register. So EAX, if it is 0, then it indicates that it has passed the test. Else, it indicates that the 80386 unit is faulty. So EAX value will be checked, right? Whenever you your hardware request for the self test. So if self test is not requested, then EAX is undefined. So we can simply ignore. And DX holds the component identifier. This is very interesting value which was basically introduced with this particular self test. So DX used to specify the identifier, right? CPU identifier. So you can simply highlight the instruction CPU ID with the 64-bit architecture, right? But here in this case, DX upon after reset, DX is going to hold, right, the product ID. So DH equals to 3 indicates it is the 386 microprocessor, and DL equals to indicates the unique identifier of revision level. So here this EDX register lower part will be indicating the stepping ID. Stepping ID means that is the revision ID, and DH in 386 case it is 3. That indicates it is a 386 microprocessor, right? Now then control register is there, CR0. Initially you can see these are basically the protected mode registers, but at this stage after reset, what is going to happen that I am telling you. So here in this case, the PG bit, all bits in the CR0 are 0, and the extension, right, this ET bit is there. So it is a coprocessor extension. ET bit indicates whether the 80387 is available in your motherboard or not. So this extension is this bit particular indicates presence of 80387. Right. So all other bits are 0, but only this bit is there. So that will be made 0 or 1 depending on the availability of or presence of 80387. Right. Then these are the default registers, right? So here you can see the remaining registers like E flags will be holding this 000002 will be the value, right? Then IP is there. Now this instruction pointer is basically going to hold the pointer value, right? So EIP will be basically that register. So ultimately this 0000FFF0, this will indicate the starting instruction. Now here this particular processor, like when you are working with the 80386, right, the reset address will be FF. So all 32 bits in that case will be generated in such a way that upper 7 digits will be F. Yeah, upper 7 digits will be F. So the physical address that is generated, and the lower digits will be 0, right? So ultimately, whatever the reset address that is called along with the Intel microprocessor, that is always having lower digit as 0 and upper digits as F. So ultimately, when you are if you compare 8086, in case of 8086, 20-bit physical address was there. So in that case, reset address was FF0. But when you are talking about 80386, and in that case 32-bit address is there, so upper 7 digits will be FFFF, FFF. So upper 7 digits are F and the lower digits is 0. So that is the reset address. And you can see the segment selectors CS, DS, ES, SS, FSGS all are holding 0 bar. And then IDDR is there, interrupt descriptor table register, IDD register. This is basically going to point to the real mode interrupt vector table. And in case of real mode interrupt vector table, it starts at the starting address or memory address. So ultimately, the base address is required to be 0, right? And limit field is there. Limit field that indicates 3FF. This 3FF indicates the size of IDT. No, so 3FF will be indicating the size of IDT, right? So here these are the initial values after reset, and all registers not mentioned above are undefined in case of 386. All right. So here you can see the registers. Now this software initialization is not required, but here in this case, I will just highlight about the first instruction, the last line of this slide. So first instruction will be available at this location FF, 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 F0. So I told you 7 digits are F and 8th digit is 0. So ultimately, this FF, 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 F0 indicates it is a reset address. So whenever you reset your microprocessor, the first instruction will be always executed from this instruction, and we can identify this particular instruction in the ROM area, right? ROM area. Why ROM area? Because there are some default operations which are to be carried out, right? Then all memory test will be there, right? Then executing the bootstrap routines are there. Then transferring the control to the no, operating system. So here in that case, all that initialization process are expected to be executed as a default operation. So that's why this ROM address, this particular address, reset address is always there in the ROM with the standard machines, right? But if you want to design your own system, in that case, you can have, it is expected to be there in ROM, but ultimately you can write your own code, right? To perform the different, default operations, right? The self-test are there and other operations are there. So you can write your own code. But generally, in your hardware, like in PCs, this this address must be there in the ROM. So always it should perform the same routine, right? Same execution of the code, right? So whenever you power on your machine, always it displays the product product logo, right? So if it is a brand, Dell brand, then it will display Dell. So that default of process program will be executed with.